So I will move to the point where we can go on from. So now, to conclude everything, I would like to consider a real example. This real example is using different NMR techniques on some samples of wetted cellulose. So, you can use, there are lots of products, lots of different materials where cellulose is playing its significant role. And here we are going to consider, I don't want to do 6, 7, 8 samples of cellulose that were having different humidities. On the typical FID signal recorded with the magic sandwich echo, it has fast decaying component, and then it has oscillation and slow decaying component. So I think after all today discussion, this we understand that fast decaying is something rigid, something solid, and slow decaying is not really solid. It can be liquid or whatever. And coming back to beginning of today, we are going to consider different methods. So first, we have measured the crystallinity, and then hence we also measured amorphicity using the second moment. Second moment, we already discussed this, using the fitting of the function with a certain model. And then we have calculated the contribution of crystalline part that is becoming lower with the increase of relative humidity of sample. In practice, this is something like the water is trying to penetrate inside the structure of sample, and it comes between microfibrilic structures and make them more movable. And so the contribution of surface, which is actually the more amorphous part of carbohydrate tissues, is increasing. So amorphous part is increasing and a crystalline part is decreasing. This result is going from the measurement of the FID, free induction decay. So this is first result. Then we try to analyze these samples. So Maria today mentioned the spin diffusion measurement of domain dimensions. Then we implement the sequence that is used to observe the polarization transfer. I can just remind you the idea of the sequence is that we kill completely the short component by 2 pulses, and then we see how the magnetization of the long component is being transferred back to the short component. So this long guy is going down, but in the same time the short component arises. And the way how we lose the magnetization can be plotted versus the square root of the spin diffusion time. And then there is the technique that is used, so-called these times of t in the power of 0.5. And this can be used to, after some calibrations with spin diffusion coefficient, to estimate the dimensions of something, dimensions of the spreading of magnetization from the amorphous part, from something that is on the surface, deep inside the crystalline. And so we have acquired these decays, and then varying water content, this parameter was varying, and the depth of traveling of diffusion, of spin diffusion, was estimated. And you see here the crystallinity goes down, amorphicity rise up. And the next experiment, which is absolutely different and uses absolutely different physical phenomenon, it tells us that this distance towards the slit of pores is increasing. So it means with the when water arises, it penetrates inside and it's makes the additional strain within the pores, slit-like pores, and these pores become more deep, become deeper, and so looking at the structure of elementary fibril of cellulose, so there are several different models. We can see that with the dry sample, which has crystallinity of around 80%, the amorphous part of sample is just the surface, and the elementary fibrils, they are very much ordered, and they are inside this cross section, and they are totally crystalline. When we are wetting the sample, so water molecules try to penetrate inside the pores, and the content of amorphous phase is rising. And with the you can see it right here. When the humidity is increasing and increasing up to 20%, we observe the penetration depth of just something like a dimension of elementary fibrils, and the amount of amorphous part is growing dramatically. In the same time, there is a T1 parameter. T1 parameter is spin lattice relaxation time. It is growing with the growth of crystallinity. So so it decaying with the amount of water. But if we plot it versus crystallinity, T1 will grow. So this is about the mechanism of spin lattice relaxation. So then we have measured, we have lots of different data, and now we are plotting water layer thickness against the water content. Water layer thickness was measured with the same sequence, but with different parameters between pulses. So we were able to measure not the thickness of amorphous layer, but the thickness of water that is adsorbed on the layer. And of course, when talking about 5% or lower, there is no a monolayer of water. But then we see that with the rising of water content, we see the changing of the trend of water layer thickness. It means that here we, until let's say 10 or something % of water content, we observe the building up of the first adsorption layer. And then when the humidity increases, then of course other effects like capillary condensation start to happen. And then we see the different behavior of water layer thicknesses. And talking about, so this is also kind of interesting effect, but I don't think we need to talk today about this. And when we are looking at the adsorption isotherm of the cellulose, so here I depict two types of isotherm. One is measured with the weighting method, but with the balance, and the other with the NMR, just estimating the contribution of the lone component which corresponds to water. And here we can see what's going to happen with water, with crystalline, and with amorphous part during humidization. So and here I again depict the same. What is happening with the crystallinity, and what is happening with the amorphicity, and what is happening with water content. So the idea is that we have implemented the different techniques, T1, then MSE, then the lone component, and then spin polarization transfer, and got some pictures what's happening on a complicated sample. So this is somehow I want to. We can talk a lot about this. So the main idea that when you are starting measuring some unknown samples or something new, you need to do some preliminary measurements and then think which types of experiments can be informative for your samples and for your tasks. And here we actually try to develop more or less simple algorithm what to do with a known sample. So first, I suggest for everybody, if you have something unknown, first look at the FID, and then does it have fast relaxing component or not? Fast relaxing component of solids can happen only within this time and range. If it has, then we process it like the solid. And we try to measure T1 for both fast and slow components. Maybe we can get from this T1 different behavior, and then we can try to estimate crystalline dimension and crystallinity. Then you can estimate the same crystallinity, water content or liquid content or whatever, measuring the FID by Magic Sandwich Echo. Then you can implement the polarization transfer experiment measuring spin diffusion to estimate some domain sizes. And of course, you can implement double quantum, multiple quantum experiments to try to estimate, to characterize somehow the correlation function of molecular motions. But if your sample does not have short, fast relaxing component, then things are quite straightforward. You measure T1 and you measure T2. And if you have some contribution, some phases, you can try to estimate their populations and try to think about their mobility. But normally for the soft and liquid components, the correlation function is quite straightforward. It's more or less exponential. So this is, I guess, how to turn it on. I don't know what to do. Oh, sorry. This is, I guess, from the theoretic point of view. This is all. If there are any questions, I would like to start answering and start discussing.
Leonid, I would like to raise one question before we just move forward to the audience. My experience is that quite often, despite investigating the FID signal very carefully, one gets single exponential spin lattice relaxation. And in some cases, it is surprised, in some not. However, very often, much more often than for spin lattice relaxation, we get B exponential or non-exponential spin-spin relaxation. This happens even for relatively simple samples. For instance, if you take fluoraniline, this is what we learned by, we just investigated that, and Adriana can say something about it. Although you have proton and fluorine nuclei, hydrogen and fluorine nuclei in the samples, in the system, the relaxation theory tells you that for such systems, in principle, spin lattice relaxation should be exponential. Okay, it's single exponential in our case, despite a lot of effort. I think it might be like that. I try to encourage Adriana to check theoretically the predictions, but well, I think we still have to work on that. However, focusing so far on experiment, the spin lattice relaxation is single exponential, spin lattice relaxation is B exponential. And this is a kind of special case of proton fluor system. However, even if you have only protons in your system, quite often spin lattice is single exponential, spin B exponential. This is physics.
Different exchange times.
Sorry?
Different exchange times.
The exchange time is like it is.
Normally, spin lattice is much longer, and then exchange might happen within the relaxation process. And for the spin, if you are talking about bi-exponential behavior, what ranges of T2 do you get there?
So you just mean like that the exchange, of course, it is like it is. However, it is short compared to spin lattice relaxation.
Mm-hmm.
But not short compared to spin-spin relaxation.
Yeah.
So in principle, the process is bi-exponential. However, yeah, it's averaged out by exchange processes. But the thing is that this applies if you have a system like, I don't know, I could agree with such an explanation if you look, for instance, at hydrated protein or something like that, yeah?
Mm-hmm.
However, what if there is no exchange? Because actually, if you take fluorine, for instance, there's no exchange between proton and fluor or anything like that.
Mm-hmm. Yeah, but we are talking about exchange between equal nuclei, not between proton and fluorine. But you know,
there's no heteronuclear exchange.
I can tell you from our experience. So we are dealing a lot with carbohydrates. For example, you can take starch, and the starch, which is air dry, in air dry condition, you will see the fast decaying component, you will see slow decaying component. Slow decaying component can be actually converted into a couple of exponents. Then when you start measuring T2, of course, you have very fast decaying, and there's nothing you can do with this. And it has different T1. But maybe you don't register it. But even for the long component, it has different T1. The long component of the T2 has different T1 from the short component. But it will be mono-exponential for T1. It will be bi-exponential for T2. That's because of the ranges are very different, and somehow the exchange might happen.
Yeah,
So
let's understand it in, I agree, in terms of exchange processes. Yeah, if the exchange occurs on a time scale shorter, much shorter than T1, then you have a kind of average effect. But as I said, this happens for heteronuclear systems, for which there's no exchange, because the system itself is very simple. Just take fluorine.
But you have only one type of protons there.
Yes, I have proton and fluorine.
But talking about protons, are they all in the equal condition?
Exactly.
But since you're observing double exponential decay, they are not equal.
Adriana is writing something I do not understand. Also, in high field, the sample was two different environments. What do you mean by two different environments? And why environment depends on magnetic field? What do you mean, Adriana, by environment?
Maybe the environment stimulates or prevents the motion.
But Adriana, we are talking about the deuterated fluoroanilin. So you have only one hydrogen atom per molecule and one fluorine atom per molecule. And they are in pretty symmetrical positions. And you have exponential T1 and double exponential T2. And this is something what I cannot get.
Are you sure that deuteration is 100% done?
90.9. It's never 100%.
I mean, when you are deuterate a sample, there are always guys who do not exchange with deuterium.
Adriana, you said that partially deuterated molecule both are mono, not be exponential. Do you mean T1 and T2, or just proton and fluorine relaxation?
Partially deuterated molecule, both mono and B exponential.
Yeah, but I do not know what Adriana has in mind. Does she want to say that? Yeah, but I know that T1 in both cases is single exponential for hydrogen and for fluorine. However, we are talking now about T2. And T2, as far as I remember, is not single exponential. Could you confirm or deny?
I guess in any situation we can just connect and see what's going on. Is Adriana now in Poland?
Yes, yes, yes.
So we can try to figure out what's going on.
Yeah, so she answered T2 is B exponential for hydrogen. And is it also B exponential for fluorine? It must, because otherwise they're pretty symmetrical, the positions.
So it is still like Adriana is measuring fluorine with spin track.
Yeah.
Fantastic.
Is this ironic or?
So normally but since it gives some signal, that's funny.
Well, are you sarcastic or you
No,
really?
no. You know, the probe can catch fluorine, but you know the pulses and all the tuning. So the system is tuned about 1.5 megahertz outside. So if you are getting fluorine signal, this is really great.
We do.
So T2 in 19F is difficult to measure. Yeah, it's exactly difficult because you cannot set up the right pulses.
Yeah, and the way you get sufficient magnetization to get the
signal. And the pulses are not correct. Pulses must be really long to have 90 and 180 degrees. That's why I'm not sure that. So just to observe the signal, it's possible to measure precise T1, T2. It will be influenced by lots of factors.
Yeah, so let us forget about fluorine, but for hydrogen, it is also be exponential, T2.
So we need to look at data and to look at the scales of these relaxation times. That can give us any guesses, any ideas.
Because it's hard to explain from the point of view of the relaxation theory. Okay, I'm not taking more of time on for that kind.
But talking about exchange, there are different ways of exchanging. You know, that's why it's not. Of course, well, different circumstance. But are you sure that your sample is monotonic? Is just homogeneous? You know, it's very you know that this took 3 hours of measurement. Yeah, of course, that's not no. So let's do the following, Adriana. You can write, and we will respond. We will discuss it. That's interesting always when we are facing some challenges. So talking about everything. So we have made some not short discussions about different approaches in time domain NMR. We have made some funny shows. Then we need to come to some conclusion what to do next. But with this, we need to have discussion.
Sorry for interruption. I have feeded the Han Echo Decay for cheese.
Oh, okay, great, Masha. So I'm stopping sharing. You can share
in Relaxed and in Origin.
So can you share your screen?
Yes.
Then you can
Okay.
magnify the initial part.
Yes.
Yes, Danuta, you can see now.
This B exponential decay.
Yeah, and it's fitted quite nice. So Danuta, do you see?
Yes, I do see, but it should still go further and further in time, yeah?
Yeah, yes, but we were discussing how
The beginning, yeah.
how well it is fitted in the beginning. But
And,
you know, for such
in origin,
complicated, you know, for the cheese, it should be distribution. It's not like you have two exponents. It should be definitely the distribution.
yeah.
Okay, this is in origin.
And the same in origin.
Yeah, well, we
So
have
the same T2 values and the same results.
That's logical. So, Kahimga, great job. Masha, great job.
So guys, do you have more questions? I will stop recording.